welcome to our next session in our GSHPA webinar programme. Today we've got Kneale talking to us about the importance of flow and return temperatures on heat pump performance, COP. So really looking forward to that. So thanks to Ken for volunteering to do that today. Just while waiting for people to join, I thought I'd give a quick overview of some of the next sessions we've got coming up. So next week we have got Shane McDonald from Calibrate Energy Engineering. He's going to be talking about the heat chill product that they sell, or the systems that they sell. So it's not a sales pitch as such, but it is very much sharing of case studies and experience in that market. So they operate primarily in the dairy, grain and potato market. So it's very rural, farming based. So it should be really interesting because that is a great area for deployment of heat pumps for both cooling and heating. And then following that, we have got John Findlay from Carbon Zero talking about 20 years of open loop systems in the UK and his experience of that. So loads to learn from that. We've got another few coming up. We've got Chris Toes from a utility team. We have got David Boone from the British Geological Society. On the 3rd of September, we've got Edward Thompson talking about fiscal background and how that is a barrier to renewables deployment, i.e. gas is cheap, electricity is expensive, and what can be done about that. So we are now booked up until early October with different sessions, which is really, really good. So of course, if you're watching this on catch up, these will always be on catch up on YouTube. So yeah, plenty to learn about, and as usual, if anybody out there would like a particular session covering by somebody, then please suggest it. Either email us at the GSHPA or get in touch with us personally, because we'd be really happy to put together some specific training or information for you. So with that, we are at 4 minutes past 1, so I think I'll probably hand over to Ken, and there'll be plenty of time for question and answers at the end. Please, as usual, put them into the chat. I will be monitoring that on behalf of Ken. So yeah, over to Ken.
Good afternoon all. Firstly, can I thank the Ground Source Heat Pump Association for the to present this webinar, and also on behalf of Solid Energy, can I thank the association and Being Beanland and his colleagues for the help that's been given over the last 3 years. Solid Energy are Danish heat pump manufacturers, and we're new to the UK, and we receive great assistance as we've become more familiar with this expanding market. The subtitles to this presentation could actually be back to basics. Press the reset button. We all know that the best principles are fabric first, but it's about resetting the low water temperature reset button to move away from the high flow and return temperatures that we have at the moment. My background has largely been on the dark side of the industry, installing and repairing large commercial heating installations with oil, gas and indeed biomass boilers. So my legacy on the planners will not be good compared to those who have been in the heat pump sector for many years. As a maintenance solve the problem quickly and to keep the occupants happy, we would very often turn up the boiler temperature and possibly even increase the speed of the pumps to come up with a quick remedy. Not obviously the best long-term solution. And when we were replacing large boilers, we would very often oversize them just to be on the safe side, with very often little cost. So that's where we've come from, and what I want to do this afternoon is to quickly suggest where we should be going to. This webinar has been put together and has previously been presented to general practice M&E consultants and to energy and facility managers for large public and private organisations to give them an overview on how to procure successful heat pump projects. It is not intended for those with doctorates in heat pump design. There are specific references to mine water and the benefits of high temperature water, but the principles of the need for low flow and return temperatures will clearly apply to all heat pumps in all areas of deployment. To assist engineers, Solid Officer Carsten Peterson has devised our heat pump selector tool. It's very useful with very basic site information entered into it. We can come up with the optimum heat pump for that specific project. It has been developed and refined over the last 2 years and found to be particularly useful at feasibility report and preliminary design stages. It is freely available to design engineers and energy managers. And I've used this tool now to demonstrate the impact of high temperatures on heat pump efficiency. Don't strain your eyes. We'll have a close-up of the relevant graphs in the next slide, but our calculator is a complex spreadsheet. We can populate the project information provided by the customers to design the best possible heat pump, single or cascade units with different refrigerants and pressures to ensure the highest possible COP. This slide actually only shows a small section of the spreadsheet. It's actually from an older version. It's now been an version which I'll show you later on is specifically for the UK market. What we have here is a 500 kilowatt heat pump, a water source heat pump, and all we're going to do is change the flow and return temperatures to show the impact on the COP. All other factors will remain the same. This is a close-up of the two graphs that are relevant. The left graph has got 3 lines. The green line shows the electrical input, just below 200 kilowatt. This would be a 170 kilowatt heat pump, and that's measured by the electrical input. The red line is the heat output, and that is just over 400 kilowatts on this graph. And the black line running diagonally is actually the heat demand from the system that this heat pump is connected to. We're showing here a water temperature coming to the heat pump from the ground of 10 degrees C with a flow of 85 going in and a return of 75. Now, this is not unusual, these temperatures. It only delivers a COP of 2.3, not even good enough for an RHI application. I'd just like you to look at the graph. The area above the red line and below the black line on the left-hand side, this shows the area that the heat pump cannot deliver sufficient energy to the heating system. And it shows that on this occasion, somewhere around +1 degrees C, there would be a need for additional heat source to implement the heat pump. The graph on the right, the blue line, a consistent COP of 2.3, I will show you later on, just for reference, a graph from an air source heat pump that shows the difference in COP at different air temperatures. The next slide, we've kept everything the same, but we have a flow of 70 now and a return of 60. It's risen to 3, and the heat load now can be managed by the heat pump to a temperature, an air temperature of -3. So with absolutely no other alterations other than the flow and return temperature, we already are seeing improvements in the performance of the heat pump. We're now on to the improvement continues. The water source still at 10. The electrical input remains as 170, and the COP is now at 3.25. I've got some figures later which will show how this increased efficiency does in fact save huge amounts of electricity costs on the lifetime of the heat pump. And the heat demand now can be met down to a temperature of -5 degrees C, which would cover most parts of the United Kingdom. Progress yet continues further. We now have a 70-40 flow and return, COP of 3.5, and a heat demand now to be met -7.5. A further rise of COP to 3.75 is met is a result of a 60-40 flow and return. And here at 60 degrees, we can have the additional advantage that plastic pipework can be used to reduce installation costs on the heating system. So to summarise all that, those 5 previous slides. I've added a 6th line in here just to bridge a gap. We've got the water temperature at a constant 10. We've got the flow temperatures varying from 85 down to 60. The return temperatures down from 75 to 40. The COP going up from 2.3 to 3.75. And if we start off at 15 pence per kilowatt, we can turn that into 6.5 pence per kilowatt as the poorest flow and return temperatures. But when we get down to the preferred flow and return temperatures of 60-40, we can actually save 38% savings, a phenomenal number. Now here we've got a water temperature of 20, which is at the top range of the water available from mine water in the UK. 60-40 generates a COP of 3.6, and the higher source water can contribute to COP, but this can be lost with a high temperature and a high flow temperature and a poor delta T. There's a summary of some other numbers that we've got. So even with a high incoming water temperature of 20 degrees, we can save huge amounts of electricity if we get that flow and return temperature correct. And there we have a summary of all the calculations that we've done on our heat pump calculator. We can see that we can make massive electrical savings if we invest in proper controls to maintain low flow and return temperatures and to get the heating services correct and the pumps settings, the design and installation stage will be worth it to generate those savings. This slide has been put in just to show the difference in the COP with an air source compared to ground source. The big difference, of course, is the fluctuating COP and also the fluctuating heat output from the heat pump. Of course, as the air temperature decreases, so does the COP. And in fact, you'll also notice there's the small drop in the centre of the COP line. That is due to the de-icing cycle, which is essential at temperatures below 5 degrees. This is the front sheet of our new calculator. If the site information is entered into our new heat pump selector, figures can be changed to predict the performance of the installed unit with all the product data, including the COP, the physical dimensions of the units, the noise levels, whether spin or indeed triple compressors are needed to deliver the highest efficiencies. The map shows the locations of the weather stations where we have collected the weather data and incorporated it into our calculations. And of course, this information is absolutely vital for air source heat pump design, but it's of course critical to for ground source. Lastly, just to digress a little bit away from flow and return temperatures and COPs, once we have the lowest system design temperatures possible and a heat pump that delivers the highest possible COP, we also need to size the thermal storage. And we need to do that for two reasons. One reason is to extend the on-off cycle of the heat pump, keep it running for long periods of time so that we extend the expected life of the components of the heat pump. But secondly, especially if we can have the space for additional thermal storage, we want to use low-cost overnight electrical supplies, which can contribute to the financial viability of installation. And this thermal store calculator, which again is readily available, is really useful to size the heat pump, the thermal stores to both help the heat pump and to help the costs of the running of the heat pump. So that is it. If we have any questions, Laura, I'm very pleased to take them.
Yeah, thank you, Ken. That's really good, really clear. Thank you. And yes, there are quite a few questions coming through, which is great. So thank you, everybody, for putting those on. Just a very quick question to start with from David Kennedy. Who can get a copy of the solid heat pump tool?
Thank you, David. Yeah, we are quite happy to release the tool, and I would suggest that in this instance, anyone that's listening, if they go via the Ground Source Heat Pump Association info email address, I'll make sure that any inquiries that come through are responded directly, and I'll issue them out.
Okay, thank you. Okay, so just quite a question from early on. For the examples being used with water at 10 degrees, what refrigerant is being used, and what is the evaporation temperature of the refrigerant being used? So 2 questions there.
Right. The refrigerant is being used on all the heat pumps in the selector is actually propane and isobutane our first stage compressors, which go up to 60 degrees, are always propane. And if we have to go on to twin and triple stages to take the flow temperatures above 60, we will use isobutane. The evaporation temperature on the heat pump that we were talking about then was 28 degrees.
Okay, thank you very much. Yeah, so the reason for the ability to go for wider densities and higher temperatures is because we're using that different refrigerant. Is that right?
Absolutely, absolutely.
Yeah. Okay. So then I had a question. What is the maximum temperature you can get from a solid energy heat pump? And secondly, if you try and ask the heat pump to do 120 degrees C in the calculator, will the calculator fail and tell you you can't do that?
Yeah, yeah. The highest temperatures that we can go up to using hydrocarbons is 90 degrees. We can reach 90 degrees. It unfortunately means that the COP reduces. We don't want to go to 90 degrees, but we can do so. If figures are entered into the calculator that are impossible to reach, which would be above 60 for the propane units and above 90 for the isobutane units, then the field will turn red as a warning that the numbers may be right, but they're not achievable.
Okay, that's good to know. Okay, thank you. So Simon has a question, and you may have touched on this after he put the question, but Simon, if it hasn't answered the question, then please let me know. He's asking, what impact will heat storage and time of tariffs have on the most desirable flow temperatures?
Heat storage is not going to affect the flow temperatures. I would suggest the flow will be dictated to by the requirements of the heating heating scheme. The water will be stored at the temperatures that are dictated to by the scheme. The intention of the thermal storage is to allow for long lengths of time so that there's not a rapid on-off cycle, but also to bank up the heat overnight so that the system can actually be fed during the day by the thermal storage, which allows the heat pump to operate when the electricity costs are low, more often than when the electricity costs are high during the peak times.
Yeah, brilliant. And I think that's such an important aspect of having a thermal store is your ability to shift when the demand is from when you're generating. And I guess that if you've got solar PV, you can also then generate, you can use a thermal store when the sun's shining and then release the heat when it's not shining.
Or dare I say, sites with wind turbine. Rather than able, you can make sure site that the thermal stores are all full whilst there's basically free electricity available.
Okay, so just going back to the flow temperature, because that what you just said there, Ken, was sort of what I was thinking as well. But if you had a time of use tariff,
Octopus, the flexible tariffs really need to be used for heat pump operation. We need to do everything we can to compensate for the high electrical costs that we have in the UK at the moment. And one of the best ways is to use electricity when it is at its cheapest. And that can be done by the use of heat pumps combined with the biggest possible thermal storage that we can get on site.
Absolutely, yeah. So Simon's just mentioned about phase change materials and having thermal stores as phase change rather than just water, and that may change the need for the different temperatures, whether you need a higher temperature or lower temperature going into the phase change material. Have you got anything that you can, anything to say on that issue?
I think phase change material, the main advantage that we've been utilising it for is when there is actually limited space for conventional thermal storage. When we want to put a small but high capacity thermal storage in.
Yeah.
We have been working with the thermal storage guys.
Yeah, I agree. I think when you're looking at something like 100,000 litres of water, I don't actually, well, I'm not aware that, I mean, Robin Curtis has just mentioned Sunamp, definitely, but I'm not sure Sunamp are up to 100 metres cubed yet. With happy to be wrong though, but yeah, tanks of water is sometimes the best when you're on very, very big thermal stores. But again, happy to be wrong. Just moving on to another couple of questions that we've got. Water source heat pump manufacturers often quote a minimum source side flow rate. Is this the optimum flow rate?
The flow rate that we have in the calculator would actually be the minimum flow rate that we would expect the ground source loops or the boreholes, but there isn't going to be a huge fluctuation in the volume that we would take out of the ground because of the consistency of the temperature that's coming out, whereas with air source we fluctuate depending upon the temperature of the air. With water, the predicted volume of water that's needed on a heat pump is relatively consistent.
Okay. Hopefully, Robin, that answers your question. But with all of these, if there are further questions that come up after this session, then please do feel free to email them across, and we can field them out to Ken or to anyone else to answer. From Michael, at 20 degrees C source water temperature, so going back to mine water, it will be possible to preheat the ventilation air directly for a building. And the heat pump could be used to deal with fabric heat loss. That's a statement. Any comment on that, Ken?
I didn't quite hear the question then, but
okay. Yeah, I don't think. I think rather than a question, it's just a statement. Okay. But I mean, I certainly would agree with that. If you had 20 degrees C water coming out of the mine, and it could be possible to preheat ventilation air directly using that, absolutely. So you've got almost passive heating, and then the heat pump is used to deal with fabric loss.
We're working with the mine authority, and where they are suggesting that heat pumps are useful, we are cooperating with them to come up with the best designs. They haven't actually been speaking to me about using the water directly, but you know, the theory is definitely there that it could work.
Yeah, definitely. And I think, you know, that's a really interesting area where, you know, we're waiting to see the first project that's going, or the first large scale project that's going in, and where that's going to go next, because that's obviously a really underutilized resource that we've got. So Simon had another question which I missed actually. Ken, do you have a view on the appropriate flow temperature if there's a disconnect between the entity investing in the system, which might be a landlord, and the entity using the system, the tenant. Now, Simon, I'm not sure, because obviously it does depend on what the building is needing, but do you mean when the landlord wants to deliver temperature at a certain level but the tenant wants a higher temperature? I'm not sure. And feel free to use your mic, Simon, if you want to.
Laura, hi Ken. No, I think in our experience, lower flow temperatures are generally preferable, but there are occasions where if you want to maximize system efficiency, the price you pay is a more expensive ground loop. And if the landlord is investing in that ground loop, but they're not benefiting from the lower running costs, they're not getting a return for that additional spend. So certainly on a lot of the work that we do, increasing the flow temperature to reduce the ground array size, to reduce the project cost, sometimes allows the project to proceed. The tenant still gets a very decent outcome, much lower running costs than the counterfactual, but they're not getting the lowest possible running costs. But that's the pragmatic solution for many situations where there's a landlord and a tenant with conflicting priorities.
Okay.
Yeah.
Sorry, Ken.
Yeah. I can see where you're coming from on that one, Simon. I can understand your statement completely. And we are, as heat pump manufacturers, slightly removed from the commercial reality that you are talking about there. We are off-pump solutions, district heating schemes, particularly where we can benefit from mine water. And of course, with mine water, the water's already at the surface. There isn't the heavy engineering costs that are needed. It's already at a higher temperature than normal. So I suspect that we are in a market where other considerations are taken on board. And of course, mine water is now going to be used in some of the poorest communities in the UK, in the old coal mining areas where fuel poverty is still a real problem. So I think it's horses for courses, and I think both systems will find a home.
Yeah. Okay. Thank you to both, to Simon and Ken, for that discussion there. Michael has asked the question, presumably there'll be seasonal COP advantages to varying flow temperature in response to heat demand, or is this only applicable where there is one building or application? So yeah, seasonal COP advantages for varying flow temperatures, that's one thing. And can that only be done when there's only one building rather than a collection of buildings, I think?
No, the seasonal COP obviously is an average of the efficiency of the heat pump over the 12-month period under all conditions. It's actually calculated using a European standard. So it's the same whether the demand is from one building or from district heating, or from multi-occupied development. It is not a figure that's pulled out of the blue. It is very much based upon a very strict formula. It also includes, for example, on air source heat pumps, the cost of on the fans on the air coolers. So it's the same for all buildings.
Yeah, and I would agree. Yeah, absolutely, Ken. It's that can be done on any building. If you've got a process load, I think that's different. But if you're heating buildings, then yes, you should definitely be looking to vary flow temperature over the course of a year to increase the COP. Absolutely. Okay, that is all the questions that I think are down there. Please shout or type quickly if I've missed anything. I just wanted to make a point actually. When you started out there, Ken, most of the heat pumps that I tend to work with, I've actually been told in the past that physics means that you cannot increase the delta T between flow and return of more than 10k. And usually it's more like 7k on a heat pump, which then means that putting them into district heat schemes is quite difficult. Now, I don't hold with that 10k always, but the solid energy heat pumps certainly enable that wider delta T, which means that you can quite easily slot them into district heat schemes and be compliant with the code of practice for district heat schemes. Yep. That is a very useful aspect of the solid energy heat pumps.
Right. Yeah. I think the fact that we, although our reference both the carbon and ammonia in the UK, we are finding that there is a definite market for large hydrocarbon compressors, and they have different properties, which we are slowly but surely convincing the designers and consultants to look at the design stage.
Mm-hmm. Absolutely, yeah. Okay, is there anybody else with any burning questions at the moment?
Right, well, thank you all very much for listening. Thank you, Laura, for hosting. And if there is any other questions, I'm sure that if you go through to Laura, then I will be very happy to answer them.
Yeah, and thank you, Ken, for taking the time to do that. It's been really, really good. So